Hello developers, let's start developing with the day 7 of 2025 Advent of Code. Since this year we only get 12 tasks, which means we're more than the halfway there. And moreover, we're on a weekend, which means this is the kind of input that we're gonna get. We're gonna go through the task based on the input. So basically a laser comes into here and then we have splitters, then split them. And we need to count how many splitters will get activated. These are the splitters, the caret character. So basically almost all the splitters will get activated, but we need to find out that this one, for example, won't. So processing the input. This input seems scary, but it's relatively simple. So the input will basically, let's do a cell or not. Yeah. So it will be, yeah, let's do a cell. Will either be an S or a dot or a splitter. That's all the options, and the input is a matrix of cells. So let's change that. Do we need the type input? Not really. We can just use a matrix of cells. So instead of string over here, we're gonna say an array of cells, and now we have everything. But just what we need to do, the lines are already an array of that, so we're gonna map them and split them and return them, and that's everything we need to do to parse our input. Let's try it. Start debug 7. Let's see our input. Yeah, we got something, so looks okay. We have a method that we can use for that. Print the matrix. Let's see if we're getting what we're putting in. Seems like that. The good thing is that we're not gonna go over out of bounds anywhere, which means that we can be a bit reckless in our processing. So what do we need to do? We need to find the start. I'm gonna have an array of beam location, which is just an array of columns which have a beam at the moment. And we're gonna have activated sense splitters. That's 0, and that's a result, and that is actually what we're gonna be returning. By the way, there is no type called numbers, it's a number array. So we're just gonna go through all of the rows. Actually, we're gonna start on row number 1 because row number 0 is kind of special. So on each row, we're just going on the first row. On the first row, we don't have any splitters, and the same goes for any subsequent even row. With that, I think that's gonna be important. Who knows? I'm kind of weary after the bait and switch that we got yesterday, but yeah, even in the big input, every even row is basically empty. Anyway, for the row number 0, you know what? I will have this be a modifiable because I'm gonna need one to regenerate it all the time. So we need to find the S on the 0th row. So const first row, that's input of 0, find the S, first row dot index of and we're kind of guaranteed that we're gonna have one S and no more than one S, which is okay. So we're gonna get a value and we're gonna put that into bin locations. So for each of the rows, yeah, we're gonna get the current row, and what we're gonna do. Yeah, we're gonna generate this a new array. Actually, let's call this temps because this is gonna be quite temporary. And we're gonna loop through all of the bin locations. So if we do encounter a splitter, yes, we're gonna increase the number of splitters. And yeah, we don't need this. We're just gonna split it because we're sure we're not gonna go out of bounds. Otherwise, just continue the beam. So yeah, this time Copilot helped a lot, but this was the idea anyway. So if we have an activated splitter, then we split the beam. What is the problem over here? The problem is that as soon as we get to, where is the small input? Yep. As soon as we get to this point, this splitter will split on this location and this splitter will also split on this location, which means that we will get 4 beams and we only get 3. I think it's better explained on the side. Yeah, over here. So this, we need to make sure that this isn't counted twice. So how do we do that? Well, it's kind of easy. We're gonna say, well, beam locations are temps, but it's gonna be an array from, or we can just use the structuring, create a new set based on those temps, and this will filter out duplicates like that. After we're done, I'm just gonna say console log beams at that thing. This might even work. Let's see. There are 22 total splitters and we're actually activating exactly 21 of them. Yep, 68685579. So this is the important. We don't have 2 sevens, we only have 1 7. And we activated 21 splitters. Let's try this on the gargantuan input, which is a bit bigger. My first idea was basically to just count all the splitters and return them, but there are some cases when we don't activate some splitters. Yeah, we have lots of rows here, 141, and my calculations say that we activated that many splitters. Let's check them, let's see if this is correct. Nope. Why doesn't my copy work? Yeah, work this time. Let's see. Yes, we managed to split the beams in a nice way, so our teleporter will start working. Let's see what the second part of the problem is. Let's read a bit on it. So, some good news and some bad news. This isn't a classical tachyon manifold, this is a quantum tachyon manifold, and that's kind of important because we're gonna split time itself. Why does this mean? We actually need to count all the possible paths that a particle would go if it chose randomly at each position where it goes. So if it only always chooses left, we have this path. If it alternates between left and right, we have this path, or if it does something else, we might still get here, but this is different. So now we're gonna get some recursion, I think. It's quite possible that we're gonna get quite a big number, and the recursion will not be the proper way to do this, so we might get a solution that runs and runs and runs and runs. So anyway, let's try that. So what do we do? Let's have a function move beam that will or count moves. We don't have multiple beam location, we have a single beam location, which is a number. So I will make a function that, given a position of our beam, for example, if the beam is here, how many different ways can it go? It can go left or it can go right, and that's it. So for this position the result will be 2. Afterwards we might implement some caching, because on the other hand, note that it doesn't matter how our beam got here. We don't care if it got this way or this way, this is still gonna be 2. So if it has 100 ways to get up to here, then it will have 200 ways to get up to here. So we might need to cache some values depending on the beam location, but the beam location now won't be a one-dimensional thing. The beam location will actually be a two-dimensional thing. So this is gonna be a point. We're gonna have a row and a call. So we found the index of S, so the initial, just do a return. Remove this return, so then everything is active. So this is the column. Start. It has a row index of 0 and a call index of that many. And it's just this. Count how many moves we can make from the start. We don't need that, we don't need that. So how do we count them? So it's simple. If we are on the last row of the matrix, don't return 0, return 1, because we're there. If a row is, it's bigger than or equal, though that's no good, but I will just say is equal to length minus 1, because we're not gonna go overboard. Otherwise, we don't need the current row, but we want to find out, is there a splitter underneath? Something along these lines. Let's see what this thing got wrong, or maybe it's correct. So, I'm not gonna do this, I don't like it that way. So we're getting the next row and the current column, and we're seeing whether we have a splitter underneath us. If we do have a splitter underneath us, then we need to split that. We need to count both. So we're gonna count the left moves. That's when the current, we're taking the next row, but we're moving to the left, and we're gonna have the right moves. which is the same thing, only we're moving to the right, and then we just return their sum. Otherwise, yeah, this is not sure, this is not really needed because it's not a splitter, it's gonna be a dot, but since we defined that it can be a splitter, a dot, or an S, it says, well, I'm gonna create a if. So otherwise we just have the moves when we move just down, and that's all that we do, and return the moves value. And over here I will say a throw new error that something totally weird happened because we don't want to do it, and I will just annotate that this actually returns a number since it's not really sure. So yeah, let's do that, but let's do this. Recursion is very difficult to gauge whether it's gonna run correctly or not, but we got 40 in the very fast time. I will just remove for the first part. We don't need this console log, or actually we're gonna hide it inside the debug statement. I think I had a debug log command to actually do this. So we're gonna start this and see whether this thing returns in a millisecond or in 3 years. The problem with recursion is that we just can't really know in front of that. So yeah, I will leave this running and go and have a smoke. Well, some time has passed and this thing didn't do anything, so I'm just gonna kill it. And I already said one problem with recursion is that we don't really know what is going on. So we might debug it for a bit. We might say, yeah, let's say which is the max row that we got. Otherwise, yeah, we can just say here, if beam location dot row, you know what? Why didn't we deconstruct this? It would have been so much easier. Yeah. So we can just say row, row, whole, otherwise it's okay. Now some might say, but why do you need a point? Why not take two parameters? Because I like it this way. This way count moves looks like it's taking two parameters because this parameter is actually one set of coordinates, even if we immediately deconstruct it. Let's just check it a bit, how it works on the smaller input, that it actually returns 40. Yep. So for the bigger input, I'm just gonna say if row is bigger than max row, console log gotten to row, okay, and max row equals to row. Yeah, this is not gonna be too much of a constant. So this will tell me how far along this thing got. Did I save it? Yes, so we can run it. So it's gonna go, oh, it went quite fast to row 141, column 0. This means this is a variant that actually went all the way left, because we're calling left. But it's not going right. So we're doing quite a depth-first approach. So this is not logging too much. Let's say let calls equals 0. On each call, increase it by 1. If calls is a nice round number, which is 100,000, just write that it gotten there. Whoa! So it's not that it's not working. It is working, and it's gotten 262 million calls so far. And it's gonna need a few billions. So what am I gonna do? I will make this function to string, which will take a point and return a string and return basically the row and the column. Why? Because we don't have object equality in JavaScript, so we're gonna need to use that. And I will define a record called cache, which is, yeah, a map. Don't like maps too much. It's gonna be a record of string and a number, because then I can use a simple object. I don't like the map interface too much, because records are about just as fast and easier to work with because they're plain old JavaScript objects. So right before the returns, and to be honest, I had a bit of an evil plan why I did it this way. Before the returns, actually over here, I will say generate the key, and if we have that value already in the cache, just return it. So we cache the values, we're not gonna be doing anything more. I think that we're missing something here, but I'm not sure. Anyway, yeah, we're doing bottom up, so we're not gonna have too much problems with this. Instead of returning it, also cache it. Cache of key equals 1. Cache of key equals that many, and cache of key equals that many. Let's see it now. Let's see it again for the smaller input, because it doesn't matter how fast it runs if it's incorrect. We're still getting 40. And for the bigger input, ooh, we were supposed to go one by one, to count one by one up to this number. This is 3, 6 millions, billions, 13 trillion, something like that. How many digits are there? 3, 6, 12, 13, 14. Okay, 14 digit is JavaScript safe. So let's see if that is our correct answer. And it is, because recursion is very elegant, very beautiful when it works, but it's very hard to determine whether a certain recursive algorithm because with the recursive algorithm we have no idea whether it will run for 2 seconds or for 2 million years. Anyway, we managed to add some caching. This is also called some kind of a dynamic programming and things like that, or memoization. There are a lot of names for this technique, but you can see how much this technique made it so much faster because we were able to optimize it. So, thank you for watching. If you like this, don't forget to share, subscribe, comment, like, do whatever you want to do with it. Just mash those buttons and keep developing.